Before we wind up our discussion on Geotechnical Engineering 1, we'll try to discuss a few more problems. Question number 6. A soil specimen has 25 cc volume at its liquid limit. Find the minimum volume it can take if the liquid limit is 42% and the shrinkage limit is 20%. Specific gravity G is 2.72. So we'll try to take the help from the three-phase system diagram. You have the three-phase system diagram at the liquid limit here. So you have 25 cc given as a volume at the liquid limit, which includes the volume of water and the soil. You have the volume of soil separately here and the mass of soil separately here. Your question is to find the minimum volume the soil can attain. So the soil attains a minimum volume at the shrinkage limit, which is Ws, the value of which is given as 20%. So in short, at the shrinkage limit, what really happens is that the volume of water gets reduced and still the soil is saturated, and this is a minimum volume the entire system can attain. Let that be V2. So you have the same mass of solids remaining. The change that happens from liquid limit to the shrinkage limit is that a portion of water gets excluded. Now at the liquid limit, we are given with the water content 42% or 0.42. Now by definition, water content is mass of water by mass of solids. So mass of water by mass of solids is 0.42 here, which means mass of water equal to 0.42 times mass of solids. So based on this figure, you can say that the volume of water at the liquid limit, is 0.42 ms, because the density of water is 1. So mass of water is 0.42 ms, from which you'll get volume of water as 0.42 ms itself. So you have volume of water written here 0.42 ms. Now we know that the specific gravity G, the value of which is already given in the question, is ms by mw or ms by vs rho w, from which you can write Vs, the volume of solids, to be ms by g rho w. Ms is unknown and G is known, 2.72 already given in the question. Rho w, density of water in standard unit gram per cc, is 1. So you can write Vs equal to ms by 2.72 or 0.368 ms. Now when you look at this system at the liquid limit, the total volume is given 25 cc, which is equal to the volume of water plus the volume of the solids. So 25 cc equal to Vw plus Vs, and Vw is 0.42 ms and Vs equal to 0.368 ms from these two equations. So I have an expression for ms, and I can solve to get ms equal to 31.74 grams, which means the mass of dry solids here marked in the maroon color is 31.74 grams. Now the minimum volume, which is at the shrinkage limit, is V2. That's nothing but the volume of water plus the volume of the solids, Vw plus Vs. Now Vw equal to water content multiplied by ms, water content at the shrinkage limit. That's important. We are talking about the shrinkage limit here now. So Vw plus Vs equal to water content times ms, mass of solids, plus Vs, equal to 0.2 ms plus Vs is already known. The volume of solids remains constant. At liquid limit and shrinkage limit, they have the same volume. So 0.368 ms is the volume of solids, whereas the volume of water is not 0.42 ms but 0.2 ms, because the water content got reduced. So 0.2 is nothing but the water content at the shrinkage limit. So you have 0.2 times mass of solids, already known as 31.74 gram, plus 0.368 times mass of solids, so that's 0.568 times mass of solids, or that's 18.03 cc's of volume. So the minimum volume at the shrinkage limit, of course, is 18.03 cc. Long story short, 25 cc of the system got reduced to 18.03 cc when the soil turned from liquid limit to the shrinkage limit. Volume of solids remaining constant, the decrease happened in the volume of the water. Next question. A cylindrical sample of cohesion 0.8 kg per centimeter square and an angle of internal friction 20 degrees was subjected to a cell pressure of 1 kg per centimeter square in a triaxial cell. You're asked to find the value of the deviator stress at failure. Quite simple. You are given with C, cohesion, and phi, angle of internal friction, and sigma C, the cell pressure. So you have the expression for sigma 1, the major principal stress, sigma 1 equal to sigma 3 tan square 45 plus phi by 2 plus 2c tan 45 plus phi by 2, in which C is already given, phi is already given, and sigma 3 is already given. All you have to do is to substitute. So sigma 3, phi, and C, from which you will get the value of sigma 1, which is nothing but the major principal stress. Now, major principal stress and minor principal stress are already known now, and sigma d, the deviator stress, is nothing but the difference, sigma 1 minus sigma 3. If you recollect the figure, you would probably remember that major principal stress is the confining stress, or the minor principal stress, plus the axial deviator stress. So sigma d equal to sigma 1 minus sigma 3, that's 4.32 minus 1, or 3.32 kilogram per centimeter square. The next question is quite similar, but with one difference. A cylindrical sample of cohesion 3 kg per centimeter square and an angle of internal friction 17.5 degrees was subjected to a total axial pressure of 18 kg per centimeter square in a triaxial cell at failure. You're asked to find the value of the confining stress. So in this particular question, the unknown value is sigma 3. Sigma 1 is known, cohesion C is known, and phi, angle of internal friction, is known. You can use the same expression, but the unknown is sigma 3. So solving, you'll get sigma 3 equal to 5.28 kg per centimeter square. I would suggest you to work these all problems on your own and check whether you are getting an answer quite similar to the one that's displayed on the slide. Question number 9. In a laboratory test at constant head of 400 mm, the discharge collected in 110 seconds was 200 multiplied by 10 to the power of 3 millimeter cube from a sample of 3000 millimeter square cross-sectional area and 250 millimeter length. Find the coefficient of permeability. So this is something related to the constant head test to determine the permeability, where the discharge is given, not directly though. You are given with the discharge in 110 seconds as 200 multiplied by 10 to the power of 3. So discharge equal to 200 multiplied by 10 to the power of 3 by 110 in millimeter cube per second. The next data given is the length 250 millimeter and cross-sectional area 3000 millimeter square. The constant head value, or the head causing flow, is 400 millimeter. So you have Q, you have L, you have A, you have H. Coefficient of permeability using constant head test is K equal to QL by AH. And substituting all these values, you will get 0.38 millimeter per second, the value of coefficient of permeability. Next question. A saturated clay has a water content of 39.3% and the unit weight of 18.4 kN per meter cube. Find the void ratio and the specific gravity. soil is saturated, which means gamma sat is already given 18.4 kilonewton per meter cube, and we know the expression for saturated unit weight, G plus E by 1 plus E into gamma W, because S turns out to be 1. And since E is also unknown, you can make use of the expression SE equal to WG, where S equal to 1 here. So I can replace E by WG. So the expression turns out to be G plus WG by 1 plus WG into gamma W, in which I have the value of W, the water content, 39.3 or 0.393 in decimals. Plus I have gamma saturated already given, 18.4 kilonewton per meter cube. So I can substitute 18.4 equal to G plus 0.393 G by 1 plus 0.393 G multiplied by unit weight of water, 9.8 kilonewton per meter cube. Solving, you will get the expression for G, the value is 2.86, and since SE equal to WG, S equal to 1, W is 0.393 and G equal to 2.86, I can get the value of void ratio to be 1.12. Question number 11. A soil sample has a compression index of 0.3. If the void ratio at a stress of 2940 pounds per feet square is 0.5, compute the void ratio if the stress is increased to 4200 pounds per feet square. Also, find the settlement of a soil stratum 13 feet thick. So you have the expression for compression index CC equal to change in void ratio by change in effective stress in the log. So you have delta E by log delta sigma, or delta E by log sigma dash by sigma naught dash, or rather represented as E1 minus E2 by log sigma 1 by sigma 2. So you are given with the compression index 0.3 and a void ratio 0.5 and the stress that changed from 2940 to 4200. You are asked to get the unknown voids ratio. So of course the new voids ratio will be lower than the previous voids ratio as the stress increased from 2940 to 4200. You have the compression index, you have the void ratio, and you have the change in effective stress. So the new void ratio as per this expression turns out to be 0.454. Plus you're asked to find or calculate the settlement of a soil stratum 13 feet thick, which means you have the same compression index CC, you have the initial void ratio 0.5, and there's an increase in stress from 2940 to 4200. In such a case, how much will a 13 feet clay settle? That is the second part of the question. So you have the expression for settlement as equal to CC by 1 plus E naught H log sigma naught dash plus sigma delta sigma by sigma naught dash, where the numerator here sigma naught dash plus delta sigma dash is 4200 and sigma naught dash is the original stress that was applied, that's 2940. H is the thickness of the clay sample, that's 13 feet. CC is already given in the question. E naught is the initial void ratio 0.5. So you can substitute these values, 0.3 by 1.5 into 13 log 4200 by 2940. And the settlement turns out to be 4.83 inches. Question number 12. The liquid limit of a clay soil is 56% and its plasticity index is 15%. In what state of consistency is this material at a water content of 45%? What is the plastic limit of the soil? And the third part, the void ratio of the soil at the minimum volume reached on shrinkage is 0.88. What is the shrinkage limit if its grain specific gravity is 2.71? Liquid limit is given as 56% and you have the plasticity index IP 15%. So plasticity index IP is nothing but the difference of liquid limit and the plastic limit, from which you'll get WP, the plastic limit, to be 41%. The void ratio of the soil at the minimum volume reached on shrinkage is given as 0.88, and the specific gravity is given as 2.71. Now at the shrinkage limit, of course, you know that the soil is saturated, so you have SE equal to WG, the expression, and the water content at the shrinkage limit, W, is SE by G, where S equal to 1, E is 0.88, and G is 2.71. So you'll get the water content at the shrinkage limit as 1 multiplied by 0.88 by 2.71, that's 0.325, or 32.5% is the shrinkage limit. So you have the liquid limit already in the question, you got the plastic limit, and you've got the shrinkage limit. So you have this plot where you have the water content versus the volume, from which you can classify the soil, whether it's in liquid limit or plastic state or semi-solid state or solid state, etc. So in this particular question, the material is given at a water content of 45%. You have shrinkage limit 32.5, plastic limit 41%, and liquid limit 56%. So 45% falls somewhere in between 41 and 56. So of course you have the soil in a plastic state somewhere in this region.